We're going to get started. These are all wonderful images you see here of everything. I think most of us, when we think of natural gas, a lot of us think of cooking, heating, Bunsen burners in middle school or high school chemistry classes. This is a very large natural gas power plant. Well, actually, a really interesting thing to point out, which is never, this is, I'm ad-libbing here a little bit, is literally within a tennis court's distance of this classroom used to be a 49 megawatt combined cycle gas power plant right in the middle of the campus, and no one knew it was there. And so I've taught, like I said, at Stanford for 35 years. It was here most of that time. Stanford is part of its, so we brought natural gas from PG&E, we generated power on site and used the power and the steam on campus. The steam was used for some of the heating and cooling needs of campus. The gas of the 49 megawatts of power generation that took place, half of that was used on campus for lab electricity needs and things like that, and the rest was sold to the grid. Stanford did not own the power plant. An independent power producer owned the power plant, but Stanford had the influence and ability at the end of the life of the commitment of that plant to decide to have the plant decommissioned. But the fact, one of the really interesting things about natural gas power plants is they can be small. They can be 50 megawatts. They don't have to be 1,000 megawatts the way most nuclear power plants are. When we talk about SMRs or small modular reactors, it is at that 50 megawatt scale. That's been hard to do so far. With gas, one of the reasons natural gas proliferated is that we could co-locate it easily for electric power generation. It was quiet. You didn't have to have piles of coal or nuclear fuel nearby, so you literally could put a gas plant in the middle of a Stanford campus. So the only reason we decommissioned it is we built something called SESI, which is a big energy system on campus that is more decarbonizing than what having a gas plant was. And you'll probably end up learning more about SESI later in class, if not have a field trip to it. We're going to cover some of these topics. How does gas affect your daily life? I mentioned some of them: cooking, heating. So natural gas, so there are a few compressed natural gas vehicles that like UPS and folks like that have, because you have to compress the gas to do that, but that's a good idea. So I have a fire pit in my backyard, and that runs off the natural gas line. I heat my house with natural gas. So heating and cooling demand, a lot of the use, we'll get into the uses of natural gas some more. So we're going to talk about costs and benefits of natural gas and why it is where it is in a moment. We're going to see where it fits in the energy system. And then what are ways we can mitigate the environmental impacts of gas. So you had a quiz question on what's the biggest issue with natural gas environmentally. Do you remember what the answer was? Leakage, right? Because it's a really potent greenhouse gas. And one of the challenges of natural gas is it has a very low energy density. And so part of what kept natural gas arrested development for a long time is we didn't have the regulatory framework in our country that allowed building pipelines across state boundaries. And so we had to have a big, I say we have a disruptive innovation wave when you get changes in technology, policy, and market at the same time. And part of what caused natural gas to lift off in the US was we had changes in policy that affected the ability to move gas by pipeline. Because pipelines are natural monopolies like transmission lines. And our Federal Energy Regulatory Commission here in the States, I know in different other countries it works a little differently, but getting the license to be able to build that transmission line across various boundaries and things like that, that involves a great deal of regulation, that had to be changed. And in the 80s, we had a highly regulated prices for gas, and it took creating a market, a free market for gas, to get gas to take off as well. In order to move gas to a home, we have to build out something that concerns many environmental groups around building new houses. Because if you build, and so there's this tension is, do we force new homes to be electric only? Because the minute you put in the local distribution system of gas lines, those, are over time, there's a risk that those can leak 50 years from now or 30 years from now, that we have all this pipeline infrastructure of major lines, which I'll show in a moment, and then all these little local lines, and monitoring those. It's only now that we have the sensors, which we're going in and retrofitting a lot of these gas pipelines to monitor for leakage. That is part of the challenge. So I think some benefits of gas, it's very versatile. We're going to talk about, we use it for lots of things. It's dispatchable. It's easy to turn it on and off. Nuclear power plants take days to turn on and off properly, at least the current kind we have. It's been very helpful, as was mentioned, to facilitate, to displace coal and to facilitate renewables, because turning on a coal plant, turning on a nuclear plant is slow. The fact that we can dispatch gas very quickly to the grid allows it, other than batteries, until we build out lots more batteries, which we're trying to do, until we build lots more batteries, being able to turn on the gas when the sun and the wind aren't there has really helped renewables build credibility. So I'm trying to think there are other things that, but I think, it's a very potent greenhouse gas. There's issues around transporting it. LNG, liquefied natural gas, is complex. Pipelines are complex. So we don't have very many free lunches. Even renewables are complex, but not in the same way the fossil fuels are. So we'll dig into it here. So the significance in history, so going back, my first conscious thinking of really making gas real for me was thinking about Bunsen burners. I grew up as a kid making fires with wood, not with gas, like a lot of fireplaces today are gas fireplaces. I didn't have that growing up. This is always the graph where you just go, whoa, pie chart, dense pie chart. But this is the one you've seen before, and it has the fossil fuels on it that you've seen before, but it's highlighting the role. So gas is number 3 in the world of energy use, but look how close it is to coal. And natural gas will probably pass coal globally, okay, for global energy. In US energy, gas is number 2, and it's about to pass oil. Because oil we use for transportation. We don't use gas much for transportation, and we're electrifying transportation. So as we hit peak demand for oil, we're still going to be using gas for a while to support electrification needs until we get all the renewables and batteries out there that we need. Gas is going to be our favored backup source of power to make renewables firm. So my prediction, that's what's going to happen on the US chart. World electricity, you see gas number 2 worldwide for electricity and number 1 in the US by a long margin. Now, coal used to be much higher only 20 years ago. So in 20 years, we've seen a major shift with the deregulation of gas, both the transportation of it and the price of it, with technology innovations around very dispatchable. It used to, 20 years ago, it took an hour to dispatch a natural gas turbine. Today, you can dispatch a natural gas turbine in minutes. So just that ability to dispatch. Now, batteries can dispatch in nanoseconds. So batteries are in a whole different league of their own compared to gas. But I'm just saying gas has progressed from a regulatory point of view, from a technology point of view, and it's progressed from a from a market point of view. So these pie charts are going to change over time, and they've changed a lot during my career and life. So this is, in terms of, this is an elaboration on the lower right pie chart, US electricity, just showing the same thing, just how important natural gas is, that nuclear comes next, coal's right behind that, and solar is growing really fast. But when you're starting from a small spot, growing really fast, it still takes a long time to gobble up more of the pie chart here, or the donut chart in this case. But again, the flexibility of natural gas power plants, their dispatchability has been a major driving force in the role that it's, and coal, again, was not dispatchable. And the emissions from natural gas, from combusting natural gas, it's very clean to combust it. It's really just been the leakage that's been the issue. Whereas if you burn coal, you have coal ash you have to dispose of, you have SOx and NOx and higher levels of CO2. And so not only is it more flexible, but overall, as long as you don't leak, natural gas has been cleaner solution. And that was the Clean Air Act really helped support the switch from coal to gas. This is showing the role across the world, the US, California, and Stanford. Because as you know, Stanford, or you're going to learn more about, Stanford contracts with big solar projects out in the Central Valley for its electricity. There's some nuance and details to that. We're not going to get in on a natural gas lecture. But it shows that California, which has very ambitious goals as a state to be carbon free, this state is still very dependent on natural gas. And so how we will ease out of natural gas in California as the 4th largest nation state in the world is going to be an interesting journey for our state, but there's a very high level of commitment to do so. And ultimately, using natural gas is going to get replaced by smarter things, electric heat pumps, electric this, electric that, and that electricity over time, we will work our way towards it coming from fossil-free sources like enhanced geothermal, solar, wind, and maybe nuclear. So, but that's what the world looked like last year, and you see the natural gas mix. This is just showing, if you put things from a voter point of view or a residential point of view, how should I think about natural gas, right? Well, it shows up on people's utility bills. Most people who live here locally are either, I get a utility bill from the city of Palo Alto's municipal utility. You might get one from PG&E. If you're in the dorms, you don't see anything. But all of these utilities are buying natural gas in the wholesale market to deliver to their customers. These utilities are responsible to deliver gas services and electric services to their residential, commercial, and industrial customers. Okay. And the bigger the customer you are, the bigger the pipeline of gas you have coming to your facility. And like in many things in life, the bigger the customer you are, the better the price you get because you're buying things in bulk. We residential customers, there's all these little pipelines that come to every house, which is quite amazing. And that there's a marginal cost of that is not shared across a lot of people. And so residential customers pay more. But for your average residential bill, it's about $100 a month is what people pay for natural gas for heating and cooling and cooking and making sure they have hot showers, because a lot of homes still use gas-fired hot water heaters. So this starts to highlight something that's really important about natural gas, is how diverse it is in terms of how it gets used. So, and another way to kind of bluntly say things is coal, nuclear, hydro, wind, and solar are only used for electricity. That's the only way we use them. Now, we're in the process of electrifying everything, so then that is going to roll over to delivering a lot of services. But when you look at natural gas, it's used for electric power generation, but it's also used for heating and cooling in residential and commercial settings, and it's used in industrial settings. The transportation part is actually used to transport the gas, which we're going to get into in a moment. Remember, I talked about the compressors we have to use to keep the pressure up in the pipeline system. That's what we mean by transportation there. But industrial use of natural gas ranges from making steel, where you need high temperature process heat, that we have not had breakthroughs yet. Maybe you'll come up with them, and we're working our way there to create the same quality of heat that's electric heat versus the quality of heat that we get from natural gas heat. So whether you're making steel, whether you're taking tomatoes and making Campbell's soup, whatever it is, heat is involved. If you're making beer, you have heat in that process, and natural gas plays a giant role in that industrial heat. Natural gas is unique to have that diversity there. And you see that oil is a transportation fuel largely, and then the other uses of oil are industrial uses, and that's feedstock for petrochemicals. A lot of those uses are not energy uses. It's making waxes, it's making asphalt, it's things like that. The largest single use of oil is for transportation fuels. So this is another way, kind of rotate ourselves 90 degrees from what we were looking at before and say, let's just look at natural gas and say, where does the gas get used? So you see how little gets used in vehicles and how much gets used to move gas in pipelines. Those are the compressors. You see electricity being 40% of all gas use, the industrial use and where it gets used in the industrial sector. You see commercial use, so that's like Stanford is a commercial use of gas. To the degree we're using gas on this campus for heating and cooling, or we're using it in our labs, that's commercial use. And then residential use, the largest single use in residences is space heating. So if we electrify that space heating, or if we're like Amory Lovins, who has a highly insulated home, you don't need to heat your home. You don't need natural gas for that. So there's an argument you should challenge architects to say, design my home so it doesn't need HVAC. That changes how you insulate and what your building envelope is, right? So this is an outcome. It's not a design principle. And for instance, when J.B. Straubel, who co-founded Tesla and is leading Redwood Materials, when he built the Gigafactory in Nevada to be this giant battery manufacturing plant that needed to get built quickly so that we'd all have battery packs for our Tesla 3s, he had a design principle which says there's going to be no natural gas in one of the biggest factories in the United States. And it actually saved a lot of time to electrify things because you had to get a whole bunch of special permits and bring gas lines out to rural Nevada and Sparks that would have slowed everything down. But when you make it a design principle and say, we're going to do this without gas, and what choices do we make to get there? We have that choice. We just haven't designed that way. I think there's a point here of, in the industrial sector, we have both natural gas being used for electric generation, but also for combined heat and power. So there ends up being cogeneration activities and things like that if you're a paper mill or a brewer, or there's a lot of industries where you're doing cogeneration. You're burning natural gas, you're making electricity, and you're using the waste heat for things that benefit that industry. I kind of like this. The part I like is I started teaching this class. Let's see, I took this class here, and I started teaching it here, and I love seeing how things can change, you guys. Coal has collapsed, natural gas is rising. In like 2 more years, check this data, go to the EIA, because gas is going to pass oil. And hopefully they'll both start flattening out, by the way. So I don't necessarily want them both to continue to be going up and to the right. But just the fact that oil's flat and gas is growing really in response to our need for electricity. We are electrifying that residential using electric heat pumps in at least the Biden administration was trying hard to accelerate it. But I think part of it ends up being educating the plumbers and the HVAC technicians that it's a better solution. And part of what's tricky, it's a little bit, is anybody familiar with Teslas very much? One of the outcomes of electrifying things is the maintenance is much lower. And so some of the companies who are in the non-electric business are conflicted because they make money off the maintenance. And so to have a product that doesn't have a maintenance business is conflicting for them, right? And so that's true of heat pumps too. The electrified source of heating homes you can have smart sensors in it that can tell you, and it can be monitored remotely. It's just a better solution. But there's a bunch of plumbers out there that are HVAC people. They're really used to doing all the maintenance work. So they have to kind of get over and become believers that there is a great opportunity for them to be delivering the better, smarter technology. This is like a whole class in one slide, which is part of what we do in this class. And this is just honoring the history of when I entered the gas industry. When I took this class in 1980, gas was the booby prize. And it was the booby prize because its energy density was so low. And we did not have the regulatory support to build the pipelines. And then it became the prince of hydrocarbons because it's so clean and it's domestic. We had a lot of natural gas that we had found while looking for oil. So we'd go off and look for oil, we'd find gas, and everyone would be like, meh. We found gas, meh. And we didn't know what to do with it because the energy density was so low. And then once we could build pipelines, and once there were markets for it, then it kind of took off. So low density, here's the meh period, the booby prize period. It stayed relatively booby prize here, and I got in the game in the 80s. Everything was very vertical, heavily regulated prices. There were forced prices that you would get. If you drilled a well, you would get 25 cents for your gas in much of the country. That was it. There was no marketplace. We had conventional reservoirs. Then we started moving into this world, and this is when I started investing in natural gas, really on behalf of Stanford's endowment, and riding this innovation wave of deregulation, horizontal wells, hydraulic fracturing, pipeline build-out, and some strong environmental regulations really around air quality that favored gas over coal. Clean Air Act, how do we get the sulfur that was being burned out of the air? Diana has a lot of expertise in air quality, and some of you are doing atmosphere and energy. If you look at that history, one of the outcomes is the decoaling and the gassing and renewing of things in the electric power sector. So where we are here is more in this land of how, we've built out a lot of LNG we're going to look at, and really coming to grips now that we have satellites and drones and cameras, and we need infrared cameras or things like them to be able to see methane leakage. And so that's really where the action is right now as we deal with wild demand. Electricity demand's been like this, and now it's going like that. And gas is something we can do relatively quickly while we're beefing up our ability to build batteries and build more solar. That's part of what firms them for some of our electric power needs. So there's kind of a history of regulation. Over and over again in class, you'll hear about PURPA, the Public Utilities Regulatory Policy Act. Was the first time that it said we could have non-utility owners of power plants. And when that happened, one of the first things that happened for independent power producers was to build gas. And that's how we got a power plant a couple hundred feet away on the middle of this campus, was because of PURPA. So some of these regulatory steps involve Section 1029 tax credits. That was a tax credit that incentivized producers to drill horizontally and to hydraulically fracture in a world where it wasn't very proven yet that it was happening. And saying, look, we need gas, we need domestic production, let's go into tight, low permeability reservoirs, let's see what happens. So those existed for about 10 years and then were phased out, which is a good way to do things. Create a stimulus, and then once everybody gets over the hump, then pull that stimulus back. That was not permanent, so that was a good solution. I think a big thing in here that I got to watch was when originally a company like Shell had to take all the risk to drill for gas, but then the minute it came to the wellhead, they had to sell it into the market at a fixed price. They were not allowed to control the destiny of their gas and sell it to NG in Europe if they wanted to, or whoever they wanted to. It was a very rigid, brittle market. And really, marketplaces are really important for all kinds of things. Whether it's used batteries, which is what Redwood's doing, or whether it's, that's a whole side conversation I get into. And the more we can build marketplaces with good boundaries around them that are transparent and actually price in some of the externalities, the better outcomes we get. So this shows what's happened to natural gas consumption globally. So since 1995, so basically over a 30-year period, you can see essentially a doubling of gas consumption by region, and the list on the right-hand side of all the things that have driven that. And so those are all good things that drove it. That's all fine, but we still have to really keep our eye on this ball, which it's not necessarily easy to keep everybody focused on it. And there's a lot of people out there, NGOs, government agencies, philanthropies, a lot of it, the more transparent we can make the harm, the more likely we're going to be able to crowdsource performance on this. So this is showing what's gone on in terms of growth by sector over the period of time from 2014 to 2024. Just showing you a lot of the growth has happened in the power sector. And the other areas, if anything, commercials stayed the same or gotten more. If you see a reduction, it's largely around efficiency. And industrial, just a little bit of growth. We're actually going to see some of these bump up a bit when we look back like 3 years from now. And then you see this, really significant pivot. We thought, certainly before the shale gas revolution, we were importing natural gas. And we never imagined that, and we were building liquefied natural gas facilities to receive LNG from other countries. And when the shale gas revolution came along, we retrofitted our LNG facilities so that we would be the ones liquefying and exporting to the world. So a big game-changing moment. This is an interesting point because we say oil and gas like it's one word. When COVID hit, natural gas demand stayed very steady for the most part. But oil demand was very affected by COVID, you see here, because people didn't go to work. They stayed home. And so the amount of transportation demand for oil, see, natural gas is not driven by transportation, and people were at home, they still needed gas they needed their refrigerator running, they needed all the things they still needed. Stanford didn't use as much gas as it did when the classrooms were full, but it's kind of one point that highlights the difference there between oil and gas. There's many points, but it kind of showed up in the data. So this is pretty exciting from my point of view, is I participated in this big build out of natural gas here, but then I also we incubated a third of the wind in the country. So you see the contribution. So this is about new capacity additions over a 25-year period of time. Look what's going on with solar, look what's going on with batteries and wind, and look how small natural gas is in terms of new capacity we're adding each year to the grid. I see your brows furrowed, so tell me what's confusing.
Why has solar increased so much, but natural gas has not?
Because of cost. So solar, and it's what customers want. It's what the market wants. So the market, solar was not economic really before 2015. Land-based solar, large-scale solar. We were putting solar on rooftops, and it was subsidized for this period of time here from 2010 to 2015. But beginning in 2015, there was a pivot in the economics of solar. So land-based solar, and companies like Meta, companies like Google, companies like IKEA, companies like big petrochemical companies, they were willing to sign long-term contracts for solar because it was economic. So this is showing gas was cheaper and cleaner and more flexible than coal. If we went back further, back here, 20 years, we were still building coal plants, right? And China's still building coal plants because they just have such a big demand for energy. But China's building wind, solar, and storage as fast as they can. This is meant to show you that in terms of natural gas, there was a large build out. We're still building natural gas capacity, but we're usually building it next to wind and solar now to make the wind and solar firm. Yes?
Will there be a time when we won't rely on natural gas?
Eventually. So people started calling natural gas the blue bridge to the green future. Coal is not a bridge. Oil is not really viewed as a bridge. But gas is truly this kind of transitionatory fuel that I think electrification, where the electricity is coming, as I said, this battery is storing the electricity. We're generating the electricity from solar, from wind. You're going to see enhanced geothermal rise significantly over the next 10 years. And probably some sort of nuclear renaissance, TBD, is going to happen over the next 20 years. And combined with all that, we're going to be building a more efficient system overall, not only in terms of how we deliver AI is going to get much more efficient, but a lot of other things we do still have a lot of room for efficiency, including solar panels, things like that. There was just a break. We didn't do energy in the news today, but it's like I'm amazed that they still are making really significant breakthroughs in the productivity of materials to convert sunlight to electricity. But this is contextualizing, if you look over here on natural gas, that today, in terms of what's going on the ground, only 7% of new capacity is gas. So gas has played this big role, I think, because of the inflection in electricity demand concerns going on right now. We're going to see an uptick, so maybe next year or the year after, gas might be 10 or 15%. But I think I don't know how sustainable that is because I think solar and wind and geothermal are going to be clicking into place. Okay, so this is kind of a flip side of the coin, is we have a lot of decommissioning that we're doing, retiring of plants. And so a really important word to be familiar with, or two words, is a greenfield plant versus a brownfield plant. So when you're building something new, and this is very relevant to clean tech where I spend a lot of time, is it's very hard to commission a greenfield project. What that means is going to a site that's never been developed for anything. It's much easier to retrofit an existing facility and pull out the old coal plant and put something new in its place. Does that make sense? Because you already have your substation, your transmission infrastructure in there. And so as we watch decommissioning, or if you read articles about it, try and figure out, there's a lot of repowering, it gets called, when you use a brownfield site. You take advantage of the transmission infrastructure, but you swap out the old for the new. And we have situations based on where the electric load is. So if a new data center gets built or a new steel factory, that's new load, okay? And so then we bring power to be near that load where there's new requirement. And so there's a very important geospatiality between where is the power plant and where is the use of that power. Okay, is that a kind of sexy molecule? Does that look like coal? No. Does that look like oil? No. Does that look like a hydrocarbon liquid? No. That is methane. It's CH4. Unfortunately, it hangs out in the atmosphere for a short time, but very potently. So we're going to talk a little bit more about natural gas. You've seen this before. So it's why it gets called the Prince of Hydrocarbons, because it's so simple. These are the groovy key words you get to hang your hat on. So sweet and sour is not Chinese food here. It is there sulfur in the gas or not? And the sulfur richness of the gas is a function of the hydrocarbon source rocks that the gas came from. It was born that way, okay, as Lady Gaga would say. So, but that's from a value and from a how much money do we need to spend to clean up the gas? Categorizing, is it sweet or sour? Is it associated or non-associated? And you nailed that already. You already know that. It's not associated with oil. That means it's just a dry gas play, right? And then is it wet gas or dry gas? So does it have hydrocarbon liquids in it that make it less than 90% methane? So these are ways we tag a gas resource when we find it, and it affects our budget of what it takes to manage it. And so these are examples of wet gas and dry gas and what could come along for the ride. So now we're going to talk about where is the gas. And here is a picture that gives you a sense of it, of where production is and where reserves are. So the US, remember, is #1 producer by a long margin. That's in blue. And where the reserves, as usual, the US is not the most abundant in reserves. You look at what Russia, Iran, Qatar have. And what do those countries have in common? Who owns the subsurface? The government. Is our government innovative and entrepreneurial? Rarely, right? So it's complicated. So there you go. That's the main story here. And this is just showing you the reserves to production ratio is the dotted line. What's going on with production growing globally? Reserves are staying pretty consistent. Part of that is we're figuring out how to extract more gas more efficiently out of the ground. But the bottom line to take away, honestly, is we have plenty of gas. So again, we have plenty of oil, we have plenty of gas, we have plenty of coal. Supply is not the issue. If we burn all these things, we're not going to be in very good shape. So, but in the short run, as we're transitioning, this at least gives you a sense that globally we're okay. This shows you who is consuming gas by country. So the US is the biggest consumer and producer. China's role in gas consumption has been rising, and it will continue to rise. Tripled between 2010 and 2021. Huge commitment in China to get off coal, even though they keep building coal plants where they need to, because fundamentally they need the power. So they build what they need to solve the problem in the moment. How many people have been to China? Okay, whatever you do, find some way to go and see it, because it's really hard to understand China until you're there. The scale is breathtaking. It makes the United States feel cute and small, and their coal plants are really big, but the country is extraordinary at their energy systems. So I think I mentioned I used to teach a class called China Energy Systems. We brought 40 students to China every other year for 2 weeks over spring break. I wish I had the athleticism to keep doing that, and the dialogue between our two countries is not as welcoming on either side right now to be able to do it. So it was from 2006 to 2016. We got to see a lot of energy systems. So you saw this before in our last lecture. This shows you the rise of natural gas and the importance of everything that's not gray is because of technology and policy and markets. And this is another way to look at the same data. So this is the colorful version. And remember, see the Permian there in green, and the Eagleford and the Woodford. So the green ones, right, are the associated gas plays in green. Here's a different way to look at this is looking at the rest of the United States, not necessarily conventional, but just basically saying 3 regions: the Permian Basin, which is Texas and New Mexico; Appalachia, which is largely Pennsylvania and Ohio. New York has a ban on any drilling for oil and gas and any pipelines going through the state. Haynesville is largely Texas and Louisiana. But that shows you where most of the gas is. So 61% of all the gas in the United States is in 3 plays, is what we would call those areas. And then this is showing the role of the tight oil plays releasing a lot of associated gas that did not have pipeline capacity. We weren't planning on it. And when we developed tight oil. So the Bakken is a big area up in the North Dakota and easternmost Montana. The Eagle Ford, you see it on the map, and then the Permian is the richest. The size on the map has nothing to do with how deep and big the reserves are, and the Permian is the big play. And so that's the area. If we only had a fixed amount of money and policy effort, that's where we're having 9% leakage, according to professors here at Stanford. And that is a big problem in terms of, how do we manage that? How do we monitor that? How do we create carrots and sticks to get the operators to make money off that 9% and not leak it into the atmosphere? So this is the proved reserves just in the United States, and that Pennsylvania grew since in the last 17 years. Pennsylvania's grown 28 times. So that's the Marcellus Shale and the Utica Shale. It's a tight shale gas play that's just taken off in terms of putting Pennsylvania in a role where, it's number 2 after Texas for gas production. And then you see Pennsylvania, it's on the production side and on the reserve side. So we have plenty of gas in the US. And so this is a different Christmas tree. I showed you some others before, and it puts it on a scale. This is a pretty small well. So the bigger the well, the bigger the Christmas tree, the bigger the well, the bigger the drilling rig that's on there, right? There's a bunch of valves, some smart person getting it all set up, probably to be able to maintain from a control room. So how does the system work? Works like that. Make it sound really easy, but you go to the upstream. So one of the things we haven't talked too much about is the history of the oil business. John D. Rockefeller, who built a monopoly from the upstream to the midstream to the downstream. We don't have too many companies that we would think of as monopolies. I think Valero, in some ways, has had semi-monopoly control of refining in the US, but not full monopoly. But the upstream is where we're exploring, extracting, and producing. The midstream is where we're moving the gas around through pipelines we're going to show you more of in a moment. Another thing that we're doing is we're storing natural gas if a lot of the production is not near where gas is needed. And so we actually repurpose some depleted oil and gas reservoirs for storing gas near where it's needed at a time of use, so that when it gets really cold or really hot and we need a lot of air conditioning demand and we need to pull on a lot of gas, we don't have to pull across 3 states to get it when we need it. So this is reminding you about all those customers we just talked about, the different flavors. And so just these are common broad ideas that are used to think about the whole natural gas system. This is showing you where overlaying on where the producing areas are in gray are natural gas processing plants and production facilities. These are facilities when the gas comes up the wellbore. Very near that, you want to be able to strip out the hydrocarbon liquids so that you can deliver gas to the major pipelines at a very standard recipe of BTU content and cleanliness. So you see the standards are set up there. The energy content has to be at a certain level. You have to have a certain dew point. You have to have minimal impurities. And so all those gas processing plants you see in blue are designed to solve that problem. Another thing that's really shocking to people is that natural gas naturally has no odor. But most of you know when you walk into your apartment or your house and it smells, you say, oh, it smells like gas. It's that kind of, I don't know, rotten egg smell. And that is a chemical that is added for safety reasons, because if people didn't smell that, they wouldn't know that gas was in their house. And if you lit up a cigarette or decided to do whatever, people don't do that anymore, thank goodness. But, we're trying to avoid, bad situations. So the whole system has this utilities on the downstream side of delivering the gas. They add that chemical for safety reasons. So the plot thickens again. So here, look at all these are the major US interstate and intrastate gas pipelines. Some of these are on the surface. A lot of them are buried underground. This shows the major flows of natural gas. California, I'm not sure I'm completely fluent in this, but we import into the state of California about 80% of our gas. We have very little domestic production of gas. Up in the Sacramento Valley area, there's been some, but that's largely depleted. So we've been bringing gas from Canada and gas from the Rockies for a long time. And you remember, over a third of our electricity in California is coming from natural gas. So that's a really important, trade stream for us, is where do we get the natural gas to do what we need to do? So an interesting thing that people think about, and this is changing a little bit with this here, is that, what do you do if there's no pipeline and you find gas? Like all this gas we found in the Permian Basin that is associated with the tight oil. So if there's no pipeline capacity, we can liquefy the gas, maybe, and then you can put it in a tanker on a train car. That's expensive, and there's a scaling factor to that unless you have you do it at big scale, it makes it pretty expensive. You can re-inject the gas like we do at Prudhoe Bay. You can burn the gas. You just burn it to produce the oil and just burn it, and then you're putting pollution in the air and you're kind of wasting something that has value. You can build demand nearby, like you could build a fertilizer plant. And methane is a feedstock to a lot of fertilizers. So that's a solution, is just build the industrial facility that uses gas right next to the reservoir. Or you can shut it in. You can just say, okay, great, we found gas, but there's no pipeline. We got to turn the faucet off and just hold it there till there's a market for this gas. Or there's a company like Crusoe that built up a business of saying, wow, there's all this stranded gas that doesn't have a pipeline to move it. Let's make Bitcoin using this energy that otherwise is a waste, rather than burning it or flaring it. So this is just to identify the fact that without pipelines, because the energy density of gas is so low, it's kind of you're kind of in a corner. It's tough. So this is showing that we have 1,400 compressor stations in the US that keep the gas moving at the pressure it needs to flow through this whole system. And this uses 3% of all US natural gas consumed every year to do that. And there's a steady effort to electrify those compressors, but currently they run on natural gas. So there's a lot of infrastructure that most of us, when we turn on our stove to cook a gourmet meal, we don't really think about everything that allows that gas to get to our homes. This is showing gas pipelines across the world, the big regional ones and the international borders. So this just gives you a sense of the United States as the #1 producer and consumer. We've gone to town on pipelines. Up in Western Canada, you see there's a lot of gas up there. And there's a lot of gas in Europe that is, in Asia, that is moving around, to give you just a sense of things that, most of us don't. Like when I first took this class, I was like, what? Wow. This is an overview, and you had a really good short video about LNG. The idea of supercooling natural gas to get it into a fluid state so that it can go on a tanker and it can be moved around, so that we have an alternative to pipelines for moving LNG globally. About 14% of the gas that goes into making LNG is essentially embodied energy that gets consumed. So the carbon footprint of gas that has been liquefied is significantly higher than natural gas that we are just moving by pipeline. So that's something, as we think about the global marketplace of natural gas, we're boosting the carbon intensity as we go global to try and displace coal. As again, with viewing natural gas as a bridge fuel to a land of non-fossil and batteries being the solution. So this is showing you that a third of all gas is traded internationally, about half by pipeline of that and half by LNG. And you see who are the big players, who are the trade leaders for LNG and for pipelines, just to give you a sense of movements and how the prices for LNG have been rising. This is just showing that LNG is for the first time exceeding pipelines as for global movement of natural gas. And the march of LNG, that 25 years ago there wasn't too much going on. You see, we've gone from a little over 100 to close to 500 billion cubic meters of gas moving. And I think everybody expects that trend to continue. There are significant infrastructure investments being made to receive LNG in Asia as a means to decarbonize off of coal. And there are countries like Qatar who have enormous gas reserves, 10x what the US has. And they are slowly and steadily surely investing in the infrastructure to liquefy their natural gas and put it out on the market. So this is showing here's where that 14% of LNG comes from. So Qatar and Australia right behind the US, but these are the major players who are exporting LNG into the global markets. In 2017, so it's only been 8 years that we've been an exporter of natural gas. Things change, and these are the big buyers of LNG in the global markets. So, Japan has very few energy resources of its own, same with South Korea. And China is just one big engine of economic growth and is looking for all the cleaner energy it can find. This is showing the United States' rise, again, a different version of the pictures we saw before, but who have been the players in exporting liquefied natural gas. And then this is the projections that we see out to 2030, so just the next 5 years of what's going to happen and the export capacity that is getting built. I mean, this is something to kind of, I was talking about what the issue is when you build more little pipelines to homes. This is building a lot of capacity to pump natural gas around the world. So, and how do we do that in a way where there is not leakage in that system? And how do we monitor that and have consequences, penalties for that, methane fees? A lot of that oversight is not created right now. And I think I mentioned in one of my earlier lectures, as we export natural gas to Engie, the French utility and global player, energy company, Engie is requiring that gas coming out of the United States to Europe has to be certified from the wellhead to the LNG terminal that there has not been leakage, or else that offsets have been paid for that leakage. So it's that kind of voluntary, at least, certification that I think will help this market, but that narrative is not as loud as it needs to be in a world where this is meant to show you evidence that the momentum to build out more gas globally and to continue to replace coal is very significant. This is showing you LNG import and export terminal activity, operating, construction, and proposed. The number means that at that location there are multiple plants being built. So this is a pretty massive build out of the ability to have a more perfect market for LNG. That's as of 2023. So I don't think we have a newer version of that, but if we did, there would be more on it. This is highlighting the fact that before the recent Russian invasion of Ukraine, so going back in time, 2011, 2021, Russia was supplying Europe and the Ukraine with natural gas. And there was this challenge of who are you dependent on and what is their power over you? And so there were times I used to describe the Russian relationship with Europe and the Ukraine as like having a choke chain on those countries. And if those countries did not behave, Russia would just cut off their gas. And so those countries are very conscious of that and want to diversify where they're getting their natural gas. Germany used to be very dependent on coal. They've gone off and on about whether they're going to use nuclear to get where they want to go. And natural gas is part of a diversified energy mix, but they'd rather import it from us or Qatar than to take it from Russia. Meanwhile, China's buying lots of natural gas from Russia because they're neighbors, and they will just build large pipelines to move gas from Russia over to China. So this is a good little CNN thing to watch if you get a chance, and just reflecting on the fact that any of these resources, we don't really fight over the movement of the wind or the movement of the sun, right? Or the movement of heat in the earth. But when it comes to things that are these stock resources, like gas and oil and coal, these are things that have geopolitical consequences, much the way copper and lithium and nickel and things like that, and cobalt, they have geopolitical influences too. These stock resources, they're tricky. So this is more about our imports. This is a view. Here we are in 2025. This is what's going on, and with their current leadership and administration, this is an almost doubling of LNG export capacity in the United States that's underway. So it's just something to be aware of. Most of this construction is going on in what I call I don't want to offend anybody who lives in the Gulf Coast, but if you grew up there, you know this to be true. The Gulf Coast of the United States is kind of our janitorial closet for our country. It's where all our petrochemical, Diana grew up there. She knows I use this phrase. Yeah, it's the broom closet. It's where all the chemicals get stored down there. And so that is the easiest place to build out our petrochemical and importing, exporting system for gas and oil and other things. So that's why most of it is there. There are much more NIMBY issues associated. So instead of the Energía Costa Azul, that's LNG. A lot of that's going to end up in California, but for NIMBY reasons, it's being located in Mexico, right over the border. So this is showing the role of U.S. exports growing and showing, how many facilities we have now, how many are under construction, what's coming. There's a lot going on. And Cheniere is a name. If you think of who is in the LNG space, they were really one of the first players and one of the largest players in the space. And this showcases a terminal that was originally designed for importing LNG that they retrofitted so it could export. So it was one of the first LNG terminals brought online in North America of any substance. So this is just meant to give more detail than we're going to spend time to talk about, but it at least should give you the comfort there is more increasing transparency being created about, how do we think about the emissions intensity across the LNG supply network? And if you can see where the biggest problems are, that gives room, if we're going to continue to do LNG, how can we manage it and make it more efficient? And how can we monitor it for the least amount of leakage? And this is showing another view about us being the #1 exporter of LNG in the world in a very short period of time. A lot on that. So now we're going to talk about a really sexy topic like weather. Okay, I noticed I was doing a call outside while you guys were starting your quiz. It's noticeably colder today than it was the last couple days. So this is showing natural gas storage. We have the ability in the US to move gas from where it's produced near where we might use it, inject it into subsurface reservoirs that have been depleted. So we call that gas in storage. And we can store near where gas is needed about 50 days of demand. And so that's really important. And one of the things that's less true today than it used to be, but it still has an influence, is commodities traders look to see as we go into the heating season and say, have we filled up natural gas storage? Are we ready for winter? Should it be cold? We've been having our El Niños and La Niñas and all that stuff. So weather's a little bit less predictable than it used to be. But this ability to store natural gas near the point of use is one form of storage. And then, do you guys remember what ducts are? A drilled uncompleted well. That's a later, not quite as dispatchable form of storage. That's there if we really get into a place of how do we bring more gas to market and hold gas prices in a zone, to just bring more to the supply. So that's just meant to introduce the idea of gas storage. This is showing you where our gas storage is, largely in the dark green states. And those are states where we use a lot of natural gas too. So you would expect the storage to be near the places it's going to get used. And Texas is a huge consumer of energy. This is showing you the types of storage facilities. The #1 type is depleted fields. Right here, we have 307 of them. And some of you know about Aliso Canyon, which is the big triangle down in LA. That was a gas storage facility where the cement and along the casing of one of the old wells in that gas storage facility, there was a failure there, and we had a very major gas leak that caused a lot of concerns about the integrity of well bores. So when that whole storage facility got shut down till it could be well understood and repaired. But it gives you a sense of where and so there is some government ownership of these storage facilities, but most of it is privately owned companies that focus on this is part of the midstream infrastructure of natural gas, is gas storage facilities. And so they are buying gas off the pipeline, they're storing it, and then they're selling it into the gas market. They want to do it when the price of gas is high. They want to buy low and sell high. So, but it's an inventory mechanism for gas. So how does it impact the environment? Well, we've talked about that a little bit. You've had a lot of videos about it. And there's more that you can watch here in a 40-minute video. That the biggest issue around natural gas is leakage into the atmosphere. So this is showing global sources of methane emissions and coding what's natural in green and what's caused by humans in red. So agriculture is actually a really significant, the way we conduct industrial agricultural activities is a major source of methane emissions, but energy is right behind that. And you see that oil, the role of natural gas, coal, etc. So methane is responsible for 30% of the rise in global temperatures since the Industrial Revolution across all these sources. So when we talk about natural gas, I get confused about, am I just talking about natural gas as an energy source, or is it important to step aside and talk about CH4, the molecule, and all the places it gets sourced from? And so that's what this is meant to kind of broaden the aperture and talk about all natural gas, not just the natural gas that is in our energy system. This is showing you global methane emissions from energy, just from energy by major source. So it's showing you that oil is number 1, coal is number 2, natural gas is number 3, and bioenergy is number 4. So this is global. So again, a lot of people think that managing methane emissions is the low-hanging fruit, of all the different ways we can interfere with the growing greenhouse gas emissions that we have globally. But in some ways, it's more powerful. It's an easier to access lever than CO2 emissions. If we take the U.S. and you think about what's the role of methane, this is all U.S. human-made greenhouse gas emissions. Methane's responsible for 10%. And then you take that 10% here and you say, what part of it? Here's all the sources: flooded land, coal mining, manure management, landfills. So 28% of the 10% is our natural gas system. And then you take the natural gas system and you say, wow, 60% of it is related to production. So at the production site, that's where we're having a lot of leakage in the system. And so trying to create this transparency, which is a big thing I'm really interested in on any system, is say, show what's the system, how do we map the system, and then where are all the problems along it? Because that's where innovation can take place and regulation can take place to address it. So this is not as sophisticated as if this was what you were doing as your job. We've got EPA experts here who know how to look at some of these things, but that's the beginning, is how do we make the problem bigger? This is a graphic you will see over and over again in class for talking about, what do we start with? We start with natural gas. We have upstream impacts, associated with extraction, processing, and transport. We tend to burn natural gas. This is just using it for the example of illumination and what that, what goes on in that process in terms of that whole system. And the good news is that process is a lot more efficient than coal, but it's still, these are all the places where impacts can take place. And so we look at the upstream and look at where we have issues and things that can happen that we can work on and regulate and monitor. We look at the midstream, which is relatively simple compared to coal and oil. This is simple compared to coal and oil. And, leaks are our big thing we want to be looking for. And then downstream, these are aspects. I mean, a big thing is there's no solid waste with gas compared to coal. It's half the CO2. If we have leaks of methane, no, we offset that. And it's the lowest water consumption of all the thermal plants. So this is showing flaring, which this is coming from the IEA and looking, but it's only through November 2021. So I'm mainly showing you this to show you it's being tracked to a degree. And ultimately, flaring, one of the challenges, so there's a lot of confusion on how efficient flaring is. So flaring is just combusting the natural gas so that it doesn't go into the atmosphere, is way more potent than CO2, but still producing CO2. And what we would want to be doing would be to be using all this gas rather than flaring it. So this is highlighting from the World Bank the impact of global flaring, that it's the equivalent, the CO2 emissions from flaring are equivalent to all these things, trying to draw attention to the fact that flaring is something we should do something about. But part of our challenge on our planet is we have so many problems to solve. Galvanizing resources around this particular topic is a tough one. And so it remains kind of an externality. So these are two, if you care about methane management, two of the world's smartest people on the topic are here at Stanford. Rob Jackson and Adam Brandt, they work closely with EDF. They work closely with EPA, both state and federal. They are fabulous human beings. On top of that, I really encourage you to visit with them or find ways to understand the work they're doing. And so EDF has an interactive data map showing the Permian Basin and where the leakage is taking place. So again, a big step is how do you make it visible? Then you can regulate it, or then you can crowdsource performance. We have satellites. Sadly, we lost a satellite called METHSAT that was recently launched into space. A lot of money, time, effort went into it, and I'm not sure. I'm not expert on how frequently we lose satellites, but it's unfortunate we lost that one. This is showing Rob Jackson's team driving around urban areas with lots of sensors on cars. It's not a Waymo, but it has lots of gas monitoring equipment. So in urban areas, we have a lot of really old local distribution pipelines for gas that are leaking. And so we've got to drive cars around with all this equipment on them to measure and monitor and figure out where that leakage is. And then you can go to the utility commission and pressure the utility to replace those leaky pipes with pipes that won't. But until, again, we have this transparency on the system and we know where the leak is, because it's invisible, we can't solve those problems. So this is a great slide from the EIA. Oh, this is from Wired, I guess, and the IEA, showing the opportunities we have to reduce methane emissions. This is showing advances in methane. This is the satellite, sadly, that was lost very recently. And you could see the work that was being done to identify where the emissions were. There's other satellites besides that ones that are methane specific. So, and we have a variety of civil society and regulatory efforts, both at the national and the global level. Enforcing them is really hard. So, and then we have some interesting language, all through this class, you're like, God, is it tight gas or tight oil or sweet or sour or associated or not? There's so many things to keep track of. This is really meant, you will not get tested on this. It's just so you it's like, oh, I heard about that in class, which is renewable natural gas is natural gas that's coming from landfills and things like that, and agricultural biomethane, basically. And responsibly sourced gas is gas that's been certified, that is normal, well-based methane, but has been reviewed for was there leakage along the system that it came from. And this is just highlighting that natural gas, where it fits. You can see natural gas in yellow still has some NOx and still has some water use associated with power generation from it, but it has no SOx and it has no particulate matter. And so that's why very attractive to the EPA and air quality and the Clean Air Act to use gas instead of coal. Economics of natural gas, this is kind of interesting actually. This is a power plant in Lodi in the Central Valley where we have brought students on field trips. And it turns out because of all the solar and batteries being built, this plant is not operating at capacity. And it was actually in an application process to be part of a hydrogen hub because the DOE and the Biden administration had a contest for hydrogen hubs. And this power plant was going to be retrofitted for, a whole hydrogen hub effort that I don't think happened. But a combined cycle gas power plant nonetheless. So this is showing you the way we measure the price of natural gas. It's a little bit out of date. We don't have 2025 numbers. The price of gas today, based on an app on my phone, is about $3.30. Henry Hub is a benchmark location in the US, in the Texas, Louisiana, Oklahoma area. There used to be much bigger variations in what gas prices traded at in different parts, kind of nodally in the US. We still have quite a bit of that. But up in the upper right is showing you what are the supply and demand forces that impact the price of natural gas in the US market. And it's just showing you the spot price there and how it moves around. And this is showing you spot prices for NGLs, natural gas liquids, natural gas and crude oil, and how they move over time, and kind of just giving you the opportunity if you really cared. I'm not implying you should, but the Energy Information Agency publishes a lot of data even under this administration because it is a fossil-friendly administration, so you can see what's going on in prices over time intervals on topics like this. Where are things going in the future? And this is from McKinsey, suggesting that we have not reached peak natural gas yet. And this was done in 2023. I tried to find something newer from them. I think most people would say the numbers are higher. The peak in natural gas is not in sight. because natural gas, the appetite for energy in India, in China, in the US, Russia is still robust. And until we can electrify further with wind, solar, batteries, enhanced geothermal, and nuclear, natural gas has all those positive attributes of its flexibility, dispatchability, and versatility that I talked about before. And so you see scenarios like this coming from GCEF's global report, just saying, look at up and to the right under different scenarios, decade by decade, and more than you ever wanted. So these are just in the deck for you to look at, but it's basically an up and to the right. And then just calling out this source of natural gas that I think I spoke to it briefly in one of the earlier lectures, that is not an economic resource. It is part of the resource base, but it's not a reserve, is this idea that since we are talking about natural gas, or if we get specific here to methane, there is a lot of methane trapped in ice, and that ice is melting. And there are some people who want to figure out how to commercially extract that methane out of the ice, which I'm not expert on at all. There are Japan and a few other countries have worked on that harder than some other people have. And for me, I view this more as an environmental threat than an energy resource. But it's something, if it's of interest to you, I just want to, it feels incomplete to talk about natural gas without pointing to this thing kind of over here that some people are studying, thank goodness. So we at least see it coming. As ice melts around our globe, and or that we find a way to harness this gas and use it for productive things. So I think that is it. And just a reminder, we've had a big boost from Booby Prize to Prince of Hydrocarbons with changes in policy, changes in technology, changes in markets. It's abundant. We're not running out. It's super versatile. It's very important for electricity to provide firm power with renewables for now. Its biggest liability other than leakage is its low energy density. And it is, if we're going to have 80% fossil fuels, which we have, if you're going to pick one, natural gas is the cleanest of them all. No ash and not as much stuff being dumped into the air. Thank you so much.
If you want to learn more about this topic or other energy topics, visit our Stanford Understand Energy Learning Hub for free resources, including signing up for our monthly Energy Spotlight. Don't forget to subscribe to our YouTube channel and tap the notification bell to be notified for our newest content.